Number 11, the integral from 0 to infinity, e to negative x times cosine x times dx. So I solved this in two different ways. Method one, I directly evaluated it. Method two, I did a comparison test. You'll see clearly the comparison test is much simpler if you were able to think of something to compare it to. But this integral looks super familiar, hopefully. You probably evaluated this before. This is integration by parts. So I'll skip the explanation here. You can check out the work. But it's that type where our integral right here, e to negative x cosine x dx, if you integrate by parts twice, then you'll get it back over here. So then we call it like I, we move it to the other side, and then we divide by 2. So the integral is half times negative e to negative x cosine x plus e to negative x sine x plus c. Okay, so I evaluated the indefinite integral first. And then I'm going to use this antiderivative to evaluate the improper integral up here. Okay. So we write it in the proper limit notation, limit as t approaches infinity. And then I already did the fundamental theorem of calculus. So take the antiderivative here, plug in the upper bound, which is t, minus plug in the lower bound. So that's why you see this is plug in the upper bound, minus plug in the lower bound. When we plug in 0, we get -1. So then -1, that's +1. And the half's the constant, so I moved it out in front of the limit. Okay, so how do we evaluate this limit now? Well, we can use the squeeze theorem. Remember that guy? So that's what I did over here. Okay. We can rewrite, so what did I do? I chose this one first. Okay, so e to negative t sine t. We can't use L'Hopital's rule, by the way, because sine t, it doesn't approach 0 or infinity. It oscillates between 1 and -1 as t approaches infinity, right? So that's why we can't use L'Hopital's rule. We have to use the squeeze theorem here. And in fact, if you keep using L'Hopital's rule, you'll get nowhere. Okay, so e to negative t sine t, I rewrote as sine t over e to the t, okay? But even before that, I guess I skipped that typical step I usually show. We know that sine t is between -1 and 1. Okay, so then we just divide by e to the t everywhere in that inequality, so then we get right here, okay? If I take the limit of this left-hand side, as t approaches infinity, it's 0. Take the limit of the right-hand side, that's also 0. Therefore, by the squeeze theorem, the limit of the middle is also 0. Okay? And we can evaluate the limit of this guy in the exact same fashion. Okay? It's also 0. So therefore, the integral converges to half. Okay, because this is 0, 0, so that limit is 1 times half, it's half. Okay? So that's the way to evaluate it directly. Okay? Now let's go through method 2, comparison test. Well, we can do a similar comparison like we had to do for the squeeze theorem. We know that cosine x is less than or equal to 1 for all x. Okay? So e to the negative x cosine x is less than or equal to e to the negative x, and we can simply restrict it for x is greater than or equal to 0. Okay? Notice that, well, as x gets smaller in the so as x approaches negative infinity, this will actually be bigger than this guy. So that's what we are going to restrict it as well. Plus, our limits were 0 to infinity, right? So we can just restrict it as well. And then it makes my life easy. Okay. So we can compare with this guy. And the integral from 0 to infinity, e to negative s dx, you might have did this in lecture or something. If not, this is really simple to evaluate. It converges. Since our thing is smaller than our thing that we know converges, therefore, our guy also converges by comparison test. So you can see clearly how the comparison test, if we were to think of a function that converges, that's also bigger than our function, it's much simpler, usually. Depends on the function also that we pick. Okay? But hopefully this was helpful to see how we can directly evaluate it as well to prove the convergence.